Hello again, Transitional Algebra 2. Yours truly, Mr. Pashar here. This week we're on assignment number 3. It's hard to believe how fast we're moving along here. But this week we're going to start talking about inverse functions. So you guys have, at this level, a pretty decent understanding of how functions work. So we'll review that briefly here in this lesson. But the main focus is to talk about inverse functions. And I'll try to explain that to you in a very layman's type of way, without a lot of fancy notations and a lot of real deep hidden meanings, just the basics that you need to know for now. We call this lesson 8.2, inverse functions that correspond to your book, and I'm calling this part 1 because next week for assignment number 4 we'll actually learn how to algebraically find an inverse function. This week our concern is just to understand what it is, look at it in terms of ordered pairs, which is the easiest way to do it, and look at a graph or two to be able to draw a graph and its inverse. So just as a brief reminder, we know how functions work. For example, I give my classic shout out to Dr. Ohashi at King's College from the calculus series I had him with. He always taught us that a function's like a Coke machine, so I always borrow that idea from him. And you guys know that too. So you put 50 cents into your black box, your function, and what you get out is Coke, your can of Coke, right? So there it is. So we want to introduce this idea of what an inverse function is. And an easy way to think of that idea is to reverse this process. So say, for example, you're not satisfied with your Coke, something's wrong with it. You lost its carbonation maybe, right? Or you changed your mind. What the inverse function will do for us is it will take it back, and we'll call this function customer service. So you take that Coke back to customer service and you get your 50 cents back. That's ideally how an inverse function works. Of course, there's much, much more to that. But this is the most basic idea based on our black box and Coke machine idea. So today we're going to look at functions in terms of a set of ordered pairs, and we'll be able to distinguish very quickly how we can recognize and give an inverse function based on that idea. So let's look at an example here. So I'm going to let function f of x, is going to be given by this set of ordered pairs. 1, 2, negative 4, 3, 6, negative 8, and 0, 0. So first of all, we should verify that this is indeed a function based on what we have here, and it is. Each x coordinate is unique. It does not repeat, so we're in good shape there. It wouldn't matter if any of the y coordinates repeat. That would just tell us we don't have a one-to-one function, and that's not really the concern right now. So if we wanted to find the inverse function, we denote it by putting f with this little -1 above it, and then the x in parentheses like normal. What an inverse function does is it changes the domain and range. In other words, it swaps domain and range. So think about, we had the example here. 50 cents goes in and you get Coke. So you could think it as the ordered pair of 50 cents, Coke. The inverse of that was Coke, 50 cents. So all we have to do here, and this is the beauty of this at this point, all we have to do is reverse the order of the ordered pairs and you got your inverse function. So 1, 2 becomes 2, 1. Negative 4, 3 becomes 3, negative 4. 6, negative 8 becomes negative 8, 6. And 0, 0 stays 0, 0. Because technically you do swap them, but they're identical, so it doesn't matter. That, my friends, is the beauty of an inverse function. That's pretty much the main idea. If you can understand that swapping of the x and y coordinates, you're in pretty good shape, for now anyway. Okay? So I'm going to give you guys a function here. We'll call it g. So let's have g of x is the set of ordered pairs 1, comma 1, negative 3, comma 2, 4, comma 2, and let's say 9, comma 8. Can you find g inverse? What would g inverse be? I'll give you a second to think about that. Okay, so I think you probably would see that g inverse would be 1, comma 1, 2, comma negative 3, 2, comma 4, and 8, comma 9. That would be your inverse, g inverse, and that's how we write it. G with a minus 1 in the x. This does not mean g to the negative first power, so don't confuse it. Very common misconception notation-wise. And as I always tell everybody, that's part of the darn problem with math, is just the notation itself. So hopefully you have the basic idea. That's how an inverse works. So whenever you're given an ordered pair of x, comma y that belongs to f, the inverse can be found by reversing the ordered pairs, y, comma x, and that would be a member of the set of inverse coordinates. That's it. In the next example, what I'm going to do is we're just going to kind of go through and talk about domain and range so you can understand what the domain and range sets would be in terms of inverses. So let's look at an example here. Let's say we have the function h of x, and we're going to have the ordered pairs negative 9, 9, 10, 11, 12, 13. So let's talk about what the domain of h would be. So remember, the domain is the set of your inputs, that's your x coordinates. So the domain set for h would be negative 9, 10, and 12. How about the range? What would the range be? Well, the range is your y coordinates. It's the set of y coordinates. So that's going to be 9, 11, and 13. Okay, so domain set and your range set. Now, how about if we talk about the inverse function, h inverse? Well, something interesting will happen here, of course. Let's figure out what the set's going to be. So if we want h inverse, all we do is take the ordered pairs and reverse the order, right? So this is going to be the set of 9, comma negative 9, 11, comma 10, and 13, comma 12. Easy, right? Just again, swap the x and the y. Now, for those who've been following along, this should be very easy for you, because if you understand the swapping between domain and range of the function and its inverse, you'll notice that the domain of h is actually the range of h inverse, and the range of h is the domain of h inverse, the domain and range swap. And again, we'll just go through and check that idea right here. So the domain set is all your x coordinates. That's 9, 11, and 13. And wouldn't you know, doesn't that match the range here of h? So the domain of h inverse is the range of h. And the range of h inverse is going to be the domain of h. So let's check out the range. Negative 9, 10, and 12. There you go. It's not witchcraft, just mathematics. No coincidence that things work the way they do. They just do because it's all fundamentally sound. Okay, so I would encourage you to pause the video at this point and maybe go back and rewind and see if you could do the problems that I did. But I think at this point you should get the basic idea. So I'll just step back for a moment and let you guys digest this fact. Okay, welcome back. So I have one more thing I want to talk to you about, and that's graphs. If we have a graph of a function of f, how can we use that to draw the graph of its inverse? Sometimes this is easy, sometimes it's very difficult. But we'll look at an easier example today to start with. So let's draw a graph here. 1, 2, 3, -1, -2, -3. 1, 2, 3, about 4. 1, 2, 3, -4. Now let's see, let's define f in a certain way. How about we put a point here at 0, 4. Let's put a point at -1, 2. And let's put a point at 2, 4. And I'm just going to connect the dots in this fashion right here. So here's a function. Okay? So the set of ordered pairs for x that I created is -1, 2, 0, 4, and 2, 4. Okay, so there's our graph. Now, if we want f inverse, all we got to do is reverse the coordinates in those ordered pairs. So we're going to have 2, -1, 4, 0, and 4, 2. And I'll do this in a different color so you can see. Let's go with green. So let's plot those new points. So we got 2, -1, that's right about there. We got 4, 0, so I'll have to add that. So here's 4, 0, and then we have 4, 2, which is right here. And we want to connect the dots. Now, how on earth are we going to do that? Well, here's a nice trick, and here's a fact that we know about inverse functions, no matter how complicated they may be. A function and its inverse, in terms of their graphs, are symmetric about the line y equals x. This would be a representative of a dotted line of y equals x. You know, you put in 0, you get 0 out, 1 goes in, 1 comes out, 2 goes out, 2 comes out, etc. So essentially this line right here acts as a mirror. So if this is f, these points represent points on f inverse, all we got to do is connect the dots. And you see that, doesn't that be a reflection of what's up here? That's a property that all inverse functions have, is that the graph of the function and the graph of the inverse are symmetric, or you could think of it as mirror images about this line. So this guy is looking at itself in the mirror. Always works. Now, you're probably thinking, yeah, Mr. Bashar, well, that's easy for this. What if you get something more complicated? Yes, when it's a little more complicated, it's a little more tedious to do. However, you're not going to encounter anything like that quite yet. So again, here was the graph we started with. We picked some obvious points off of that curve. To write f inverse, we just reversed the ordered pairs that were given. And using this idea of y equals x as a mirror for the inverse function, we connected the dots here correspondingly, and you have your inverse function. And essentially, my friends, that is a very brief crash course on inverse functions, but for now, that's all you need in order to do the exercises in your textbook. So I hope that you enjoyed this lesson. I hope that everybody's staying healthy and well. Again, if you have any questions, please feel free to email or call. And as always, until I see you next time, take care, be safe, and enjoy.